Well, good morning and welcome to Cosmic Conversations here on the Morrison Planetarium Facebook page. My name is Ryan Wyatt. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences. And I'll be in conversation today with Carolyn Collins Petersen, the space writer, who is a science journalist and writer who works on everything from books to a tremendous website with the latest news in astronomy, as well as exhibits. And she's a luminary in the planetarium field who's written many planetarium shows. So it's a great pleasure to have you here, Carolyn. Thanks for joining us.
Well, thank you. It's a great pleasure to be here, especially after this busy week.
Yes, right, because this has been the week of the American Astronomical Society meeting, the 237th meeting of the American Astronomical Society. If you want to sound like one of the cool kids, you call it the AAS meeting because, you can't say AAS. That just sounds weird. And it's sometimes called the Super Bowl of astronomy. It's when we meet in person, it's the largest physical gathering of astronomers in the world. But of course, it's virtual now. So Carolyn, how long dare I ask, have you been attending AAS meetings?
Well, I went to my first AAS meeting in '92 when I was a baby graduate student. So I've been a member ever since. So almost every winter meeting and several of the summer meetings.
My first one was 95, so I celebrated 25 years last year. Anyway,
I remember giving my first talk, and Vera Rubin was sitting in the front row grinning at me. So that was pretty cool.
And now she has this amazing telescope named after
Wow. Which they're talking about. Yeah.
Well, we're going to talk about some of the news stories, and to do that, we kind of have our Digital Universe software up and running. And so right now we're just in orbit around Earth, but we're going to use that to go and visit some of the locations that we're going to talk about. And I don't know, what have you found most exciting about this year's gathering?
Oh, gosh. Now that we're all used to using Zoom and using vFair, which is the platform that we use, everybody is very good at switching back and forth between talks. We've all had almost a year to get used to this. But I used to go mostly to the planetary science talks. There aren't that many at the AAS. They're usually at DPS. So I've been gravitating more towards black hole talks and high energy events in the universe. But really, when I'm writing about it, I kind of try to cover the whole thing from planetary science to cosmology, essentially.
Yeah, DPS is the division of planetary science,
right?
Which is a subset of AAS.
Right. I think that's held in the fall. Yeah.
Right, and this is like the big So there are a lot of meetings. The winter meeting, as it's called, is sort of the biggest. But it's a lot different going from Zoom room to Zoom room. I mean, it's a lot faster than going down escalators at a convention center, but not quite the same.
Yeah, it's pretty amazing. Every time I think of a meeting, I think the last one I attended was probably in Seattle, so it was 2 years ago. And last year, this time, the pandemic was really just getting rolling, so we elected not to go to Hawaii, which I just eternally regret because it would have been a great meeting. But it's like a fire hose of astronomy data, and it's what I was warned when I first went the first time. My advisor said, "Don't try to go to everything; you'll just kill yourself." And it's like you have this little bucket, and you're trying to hold up all the science into your bucket, and you just get what you can, and it's amazing. And this meeting actually had some special sessions this year, not just about astronomy, but also about other cultures' involvement in astronomy and indigenous astronomy, bringing more attention to, for example, at Kitt Peak, the local, and I can't pronounce the Stono-Ohodum tribe of Native Americans is very much involved with Kitt Peak, and they had a special session about that. They also had a very well-attended focus on the experience of being a Black astronomer, people of color in astronomy, and the challenges faced by that growing community of colleagues that we have coming in. I saw a ton of questions at that one, and people were talking about it ever after, about how useful that was. So we're trying to getting involved in. It's more than just science. It's the community and how our community is working together. I
mean, it is interesting, and since we've been talking about how long we've both attended, I've really seen a difference in the attendees at AAS in this time frame, where it's just a much more diverse community than it used to be, both in terms of, in terms of age too. I feel like I see more and more young researchers there, many more women, and just a much more interesting cross-section of humanity at AAS these days.
Yeah, I have to laugh because that age thing may be selection bias now. We're getting older, so I look at them and go, what are these 15-year-olds doing here? And they're all doing really great science, right? So
yeah.
But one thing I found was really interesting. There was one of the first talks that was given was not just about astronomy, but it was about the society that we're building and our technological advances. And Brian Nord from Fermilab founded this group called the Deep Skies Lab, and they were using artificial intelligence to analyze data, big data sets. And one of the things he wanted to bring across to people was that these tools that we're using to classify galaxies and look for exoplanets and all this sort of stuff, taking these massive amounts of data and making some sense out of them, are also the same tools that we are seeing being used by police departments and medical research and all this to separate all people, into different groups. And he just wanted us to be aware of that our tools are being used for good and for maybe not so good. And this week was sort of an interesting juxtaposition to have that talk, but that really had a lot of attendees coming to that as well, because it's the future of data analysis.
Yeah, absolutely. And it's transforming astronomy, but of course it's also transforming our society as well.
Yeah. So that's another change that I've seen happening over the years, and it's more than just the people that we're bringing in and our colleagues, but also the tools that we're using, because we have these surveys that can just go out there and in a short period of time really gather the information about the universe, and we have to now analyze that. And it's the same way with facial recognition and all the other things that we use AI for.
Absolutely.
Yeah. Well, I see you're moving us out of the solar system here.
Yeah, that's sort of the virtual nudge to keep us moving, since we do have a lot to talk about. I want to make sure that we get to those. So I think,
go ahead.
I think one of the first topics that you wanted to talk about was a talk by Alan Stern, who was the head of the New Horizons mission, and some of the work that he did with looking at Pluto, but looking beyond Pluto, helped us understand sort of this broader range of astronomical topics.
Right now, the New Horizons is headed out through the Kuiper Belt, and so it did look at Pluto. The mission discovered a great many things about this world that people really didn't know what to expect. I mean, I've heard them say we thought it would be this dead world, and it's not. The mission discovered a nitrogen ice glacier, which is very active on that world. I believe it's over there in Sputnik Planum, which we can kind of see. Yeah. And so it's an active glacier, and they found evidence for an ocean at this world, and very rich geology on this world that they really didn't expect. And so the discoveries have really raised a lot of questions about the surface materials that are on not just Pluto, but Charon and Arrokoth. And Alan was kind of bringing up the point that, there are 2 points. One of them was that all of these materials that are on the surface exist out in this very cold environment. It's not quite as irradiated by the sun as, worlds further in, but it's still being irradiated. And there's not a lot of laboratory work to nail all that down about why these things like methanol and ammonia and nitrogen are existing the way they are, and that they're forming these active geologic units on these worlds.
Right.
And one of the questions that they're asking is, why is all this occurring? For example, the planet's atmosphere is optically thick enough that it can filter out far ultraviolet radiation, yet you see this reddish material on Pluto, you see it on Charon. Why is that happening? And is there something in laboratory science that we can do back here on Earth to understand how those compounds are reacting out in the outer solar system?
Very cool.
There are very interesting terrains on Pluto. There are big mountains of methane ice that are deposited in an ongoing methane cycle. Why is that happening?
Yeah.
And so, again, there needs to be this lab work done.
So all of these features that we see on the surface of Pluto are really quite dynamic, too. I mean, in long time scales longer than human lives, but still they're changing more than you might expect in the kind of what we think of as the deep freeze of the solar system way out from the sun.
Well, and one of the things you brought up, too, is there's relatively not a lot of cratering. I mean, you see some here, but not a lot. And the younger the surface, the fewer the craters it has. And so either it's not getting cratered, which is kind of hard to believe, or there's some kind of activity resurfacing the world. So, yeah.
I should just point out that we are seeing Pluto, of course, up close here in the foreground, and then we have Charon in the background. And I think we have a picture of Arrokoth which is
Arrokoth is the second is then the next thing that Horizon went out and looked at, and it has this interesting formation history that they're still trying to tease out. Why are these what looks like two things that have glommed together? It has a crater in history, but not much of one. It seems to have experienced a number of very low speed impacts, and so how are those impacts changing the surface in terms of heating and weathering and that sort of thing? So he's calling for follow up laboratory experiments on this. The other thing that he brought up sort of in passing was all of this study can help us understand these same kind of systems around other stars, in other solar systems, if you will. And there, there's these equivalents to the Kuiper Belt out there. How can we understand them? So we are out here in the far solar system, and I guess while we're out here, we can bring up the other paper that I went to or the other session that I went to that I found was really interesting. What you see here is the outer solar system and the paths of 5 spacecraft that have gone out through the Kuiper Belt. So there's, okay, you have to tell me which ones they are.
I think I can do this. I'm pretty sure this is Pioneer 10.
Yeah.
Up here, and then Pioneer 11, and then Voyager 1 and Voyager 2.
Yeah.
And then we also have, I should note, the New Horizons spacecraft, which is kind of this high-speed zipping right out from Earth to Pluto, because it kind of went on the accelerated route out to to Pluto.
9 years to get out there, but yeah. Well, this so 4 of these have now left the solar system, well beyond the influence of the sun. And the 2 Voyager spacecraft are what I want to focus on a little bit. There was a set of paper sessions that were given about the Voyager spacecraft and what they're going to be experienced when they go out. And this was all keyed to the golden record that's attached to each one of them. So back when I was first a science writer, I had this great fortune to cover the first of the 3 flyby missions and I went out to JPL. And that's where I learned about the existence of the golden record that's attached to the side of the Voyager 1 and 2 spacecraft. Okay. And it's an encoded, there it is. Can you bring that around? Yeah. So it's attached, and there's actually a phonograph record there that has encoded on it about an hour and a half's worth of music from all the cultures of Earth, plus spoken greetings, animal sounds, and images and scenes of people on Earth. And so the record is inside this cover, and the cover has instructions about how to find us. I think that's the orbit of a hydrogen atom. And then this little thing, I can't show it to you, but there's a little thing down at the sort of the bottom left of that, which is basically showing us showing us the direction of Earth from the nearest pulsars. So
actually, that's interesting. I hadn't even thought about that, but we're going to talk about pulsars later in the program. So it's kind of great to have this there because it's a cool reminder of how awesome those objects are.
So the set of papers was really about this record, but one of them was kind of intriguing. There's a group of scientists led by a fellow named Nick Oberg that extrapolated the orbits of the Voyager 1 and 2 out into the galaxy. And basically, they're both on trajectories taking them out of the solar system. They're gone out. They're going to continue on essentially for billions or even trillions of years through the galaxy. They're going to stay in sun-like orbits, but they'll rotate around the center of the galaxy just like the sun does. They'll continue on through whatever happens to the Milky Way, including future collisions. One of his questions, though, was what's going to happen to the spacecraft? And what's going to happen to the record. And they're thinking that if these 2 spacecraft encounter any clouds of gas and dust, that there could be some damage to the outer cover of the record, but they're hoping that the record will stay in one piece. And if anybody finds it billions of years from now, they'll have a record of our time on the planet. So I found that to be a really interesting kind of topic.
Did they send a record player along with it? Or
there's a stylus on there. Yeah.
Okay.
Yeah, and one of the things they said was if anything happens to the spacecraft and it scours off the record and scours off the covering, it's possible that the stylus would be the thing that lives the longest.
Wow.
So you get to see this stylus floating around out in space. Pretty interesting.
It's definitely without the instructions to know.
Well, the instructions are a little difficult to suss out, but the main point of the records and really the spacecraft is its final mission is to transmit information about us. Once it's shut off, it's on the final part of its mission, and that is letting everybody out there know we existed, we did things. Here's our Chuck Berry music and pictures and all this stuff. It's pretty cool.
Very cool. And, and so actually we're now kind of following Voyager, although a lot faster than Voyager, is doing it out into our virtual interstellar space. So I think our next topic is getting onto a little bit. I mean, there's usually a lot of discussion about exoplanets these days at these conferences, but maybe just a little bit about some of the exoplanet discoveries.
Yeah, I think that usually we have at least 2 or 3 press conferences on them, and there were something like 5 sessions about exoplanets. And we've known about them since the mid 1990s. The first discoveries took place then, but they've been speculated, of course, before that. There have been a number of missions flown to look for exoplanets, such as Kepler, which covered a fairly small amount of the sky, to TESS, which is covering, I think, 75 or 80% of the sky to look for.
You can see
planets all around.
Kepler data over here. This is sort of each one of these little, we call them jacks, kind of represents the location of an individual star with planets around it. But yeah, it's sort of uneven coverage, but also preferentially finding these much closer to home.
And I think there's something like 26 or 2,700 confirmed exoplanets from the Kepler data. And of course, we've got TESS rolling in a bunch more. So.
And so I think what's interesting then is that now we can actually start to do statistics on these, and that's what really makes Kepler interesting. I think that was one of the cool sessions. I missed it, but I think you were telling me about.
Yeah, it was basically the hunt for worlds that are like Earth. Everybody's interested in worlds like Earth, and so one of the papers that were given outlined the search for rocky habitable zone planets. So the habitable zone is the place around a star where liquid water could exist on the surface of the temperatures are high enough that liquid water could exist on the surface of any worlds within that zone. And astrobiologists are thinking these are the places we're going to look for first. That's like the low-hanging fruit of where you would look for life. Of course, they're going to concentrate on the closest ones who is first. So Steve Bryson from NASA Ames Research Center actually did a bit of a deep dive into occurrence rates for worlds in the habitable zones, and they used this Kepler data as a basis. A lot of analysis, and they came to the conclusion that they're pretty confident. This is about as confident as you get in this little right. But that the nearest habitable zone star or nearest habitable zone planet around a G or a K-type star, like ours, so we're a G-type dwarf, is about 6 parsecs away from us. So that's about 20 light years away. And then he also went on to kind of extrapolate a little farther out, and they think that there would be at least 4 rocky planets in the habitable zones within about 10 parsecs or 30 light years of the sun. So we know that there are many, many stars within 100 light years of the sun, well, give or take 80 or 90. And this is what you brought up here, this sort of region close to the sun. This is the radio.
Yeah, our nickname is the radiosphere. So it's the sort of the bubble of expanding radio waves that represent the most distant radio emissions from human-caused radio emissions from Earth that would have been strong enough to escape the ionosphere. So it's kind of nice to provide a little bit of sense of scale. Yeah.
And so basically everybody, if there are, kind of the interesting to think about is if there's inhabited planets out there, they're getting our broadcasts at this point, and they're listening to us, I Love Lucy or Star Trek or whatever that they're getting.
I guess the other part of it is that, so many, we found so many of these planets, and yet many of them are just not at all what we expected. And so it's kind of interesting because it sort of turned the question around to, these are so bizarre. I mean, planets that are orbiting completely different from the way our solar system is put together, and planets that are much larger than Jupiter, the largest planet in our solar system. And to find the ones that are like, oh, well, how common are the ones that are like us that are kind of encouraging to look for?
Yeah, and there's been a lot of speculation about that many, and I don't remember the numbers. I remember several years ago, Seth Shostak came up with an estimate of, there are planets around every star in the galaxy, and a very small percentage of those are going to be the ones that might be able to support life, but it's still millions or billions, out there. So, when you think about it, they're out there. But you're talking about weird planets. I heard a comment yesterday at one of the press conferences that giant Neptunes can transform or lose their atmospheres in some ways to become these super Earths. And I didn't catch the rest of that, but I have to go track that down now for another story. But one paper that I did find was pretty interesting was given by Thomas Beatty at the University of Arizona. And he was looking for cloud features. And this is a little world called Kelt 1b. Kelt stands for the kilodegree, extremely little telescope.
Yeah.
And it's basically looking for transiting planets. So these are planets that go across the face of their star from our point of view. And so that's called a transit. And this is Kelt 1b. It's a super Jupiter. It's a typical hot Jupiter. And it's about 1,000 light years away from us. Somebody made the claim yesterday that it could be more like a brown dwarf star, but they're going to leave it as a planet for now. It's one of 3 in its system, and it has a surface gravity about 22 times more than our typical hot Jupiter. But anyway, the paper focused on trying to find clouds on this thing. And normally in a Jupiter, if you've got something that's facing the star, those clouds are going to burn off. They did something, and I'm just going to throw out a piece of technical language here. They did something. They used test mission data and Hubble Space Telescope to look at something called spectral variability of the planet. And they're basically how it changes in its spectrum over day to night. And they found enough data to show that it looked like there's clouds that exist on this thing. And they're basically born on the night side of the star or the planet. And as it rotates around and the clouds are blown around to the front side facing its star, and they burn off. So from night side to about morning on this planet, those clouds are there, and then they dissipate and burn off until by late afternoon, they've got clear skies again. And sort of the importance of all this is that you want to be able to look at atmospheres of planets, and it's pretty hard to do it with exoplanets. You have to look through light, look at light from the star coming through the atmosphere or something. Would give you some clues about whether or not life exists there or what chemicals are in the atmosphere or whatever. So there was a whole session a couple of sessions actually on atmospheres, and this was one of the outcomes from that.
And I should know that we've been flying around this like it's a real place, and it is a real planet, but this is sort of an artist's rendition. And so we kind of put this together based on what we could find out about about Kelt 1b, but it's a pretty highly interpretive kind of image.
Yeah,
to be clear. Well,
and it's going to be that way for a while. And of course, there are more missions going out to look for more exoplanets, so we have a lot more data to look at. And hopefully, someday we'll be able to take a picture of one. But right now, that's pretty hard to image them.
Well, so now I think I'm going to take you to a very different kind of place. So let me just go ahead and see if we can fly up to that. Sorry, doing a little bit of spinning around. I do a lot of the piloting, but I also let the computer do some piloting. So sometimes the computer is not as elegant, I think, a pilot is.
There we go.
That's exactly what I did during rehearsal. I'll blame the model.
Well, you've just been through a millisecond pulsar.
Exactly. Yeah, you've been closer to a millisecond pulsar.
So this is a pulsar, and the pulsars. Excuse me, I'm sorry. There's a visitor here. Pulsars are basically the leftovers of massive stars that died in supernova explosions, and they are also cosmic clocks. They spin very precisely, and they tick like clocks, and sometimes they're much more accurate than, say, an atomic clock. So this is a representation of a pulsar, and I think there's a whole collection of them we can look at. There's a visualization of all the known pulsars.
I like the analogy of sort of a lighthouse, and basically it's a beam of a lighthouse, and you can see it. I just want to put up the markers for this. Right. Sorry, that's part of one of our spinning jack markers here as I pull away from our target. Cool. Oh, and I'm so sorry.
Here we go.
That's a little more springy than I normally get. So just as a note, kind of what we're looking at here, and I apologize for the crazy flying. That was my fault. I can't blame the computer for that one. You'll notice that our kind of volumetric model, as we call it, of the Milky Way kind of obscures the view of these. So I'm just going to replace that with kind of a flat image. And this is not really what the Milky Way looks like, but it's just a representation that will give you a sense of where the plane of the Milky Way is, sort of where the average orbit of stars in the Milky Way is. So that's a little bit easier as we talk about the distribution of some of these objects.
And you can see that they're distributed all over the galaxy, the ones that we know about.
Right. Yeah. I'm sorry. I'm showing the kind of the 14, the ones that we're going to talk about.
Oh, there's all of them. Yeah. Good.
There's all of them. And it is pretty impressive.
But you did show the 14, and the 14 are kind of important because they're the ones that are the closest to us, and we can measure their clock ticking. And they played a pretty important role in a study that was done by Dr. Sukanya Chakrabarty, and she's at Princeton. And she and her collaborators used pulsar data to clock basically the radial, so the moving, the radial and vertical acceleration of stars within the Milky Way, but also just outside the plane of the Milky Way. And what they wanted to do was calculate the Milky Way's dark matter component. So dark matter can affect their motions. The Milky Way has gone through this series of mergers and is being influenced by the close approach of dwarf galaxies. And all of this can be measured by the effect that it has on these pulsars. So that was kind of cool. As a result of all the action, the star orbits tend to follow a path that look more and more like a warped record. And that can actually be measured. So any perturbations in those orbits are going to be due to local concentrations of dark matter. So I think basically the headline on this was that these pulsars helped show the dark side of the galaxy. Now, there was another really interesting timing result that caught everybody's attention. Do we want to talk about the structure of the Milky Way?
Sure. I was just going to say that actually, yeah, we could jump to this. Sorry, we have Josh behind the scenes who's doing the some of the producing here. But before we jump to that, I actually did want to show the warping that you mentioned.
Yeah.
And this is actually from a data set. Sorry, let me go back to our flat image of the Milky Way, which makes this again easier to see. And then we'll put up, this is a data set. This wasn't what was talked about at the session today, but it's a data set that was released about 1.5 years, 2 years ago, showing the locations of Cepheid variables. But what we like about that is it shows the kind of the warp and the disk of the galaxy pretty well.
Yeah. And there's a result we're going to get to about that too, which is just fascinating about how this warp has come about. The other thing I wanted to mention about the pulsar timing was just there's a National Radio Astronomy Observatory group called the National North American Nanohertz Observatory for Gravitational Waves, and they're looking for gravitational waves in the universe. And a couple of presentations on that also talked about using millisecond pulsars. So these are about 10% of radio pulsars are these millisecond pulsars, extremely accurate, very, very dependable. They're in binary systems where there's a material accreting onto the pulsar, and that kind of helps keep it spun up. Well, they used nanograv to study radio emissions streaming from these pulsars and found what's called the gravitational wave background. Now, that's a steady stream of gravitational radiation that actually fills the universe. And the way that they put it was that it's basically measuring all the gravitational waves that have ever happened in the universe. So it's gravitational wave background. I kind of thought of it when I first heard of that. I thought about the cosmic microwave background. Now we have this gravitational wave background. And you can think of it as us and the pulsars bobbing on this sea of little gravitational waves that are coming through the universe. And as those waves actually change our distance a little bit, and that changes the timing signal that we get from each one of those pulsars. And this was all found by measuring just tiny changes in the distance between the Earth and the pulsars as they bobbed on these gravitational waves. So they're pretty certain that's what this is, and it just is another way that we use to study the universe. We didn't know about gravitational waves until the first one was discovered a few years ago, and now we're finding them all over the place.
Yeah. So yeah, it's a super cool application of these amazing objects. And I will just note, I tried writing up those results, and it's a link to it on our Facebook page, but I think we're going to share it in that as well to try to kind of wrap your head around how weird this all is.
Yeah, I think one of the writers talked about it like a wash of gravitational waves floating through the universe. It's just one of those new things that we hear about in science that you just go, wow, I never thought of that. But yeah, it makes perfect sense. So
yeah, it's just kind of mind-boggling though. It's kind of like, you think about these gravitational wave events, like the colliding black holes or colliding neutron stars, where it's like you're looking at it's basically like a stone being dropped in a pond and you're looking at the ripples. Yeah. And that seems like a nice, neat analogy you can kind of wrap your head around. But then to think about like a really, turbulent pond from ripples that overlap one another from a whole bunch of different events, that's just a much crazier kind of thing to try to imagine.
Yeah, a lot more physics to figure out there. And I was thinking, back when I was a really little kid, black holes were a theoretical construct, and now we've got them colliding, and and there were a lot of talks about black holes at this thing too. We didn't even get to that. So. Yeah,
very true. But I think one of the things that I sort of jumped the gun, sorry, but we were sort of talking about was how a lot of talks have also focused on this sort of changing picture that we have of the Milky Way, not as this our home galaxy is not just being this very kind of scientists would say in equilibrium, but just,
Yeah.
these kind of very straightforward, understood orbits to something that's a lot more really interesting.
And dynamic. Yeah.
Yeah. So this might be a good one to jump to the, I think what Josh, you had started to show earlier.
Oh, yeah.
And this is from a talk that, this is actually from Adrian's website, but
Right.
from one of the plenary talks that we had.
Yeah, and this just shows the effects. So what he was talking about was how in these big surveys like the Sloan Digital Sky Survey and others, they're finding these populations of stars that don't kind of match what we think of as being part of the Milky Way, and they're moving in these streams, and they're all connected to each other. So Adrian Price Whalen actually showed the effects of these streams of stars that are flowing into and out of our galaxy, and they were pulled out during close interactions with dwarf galaxies. And the PAL 5 one is actually from the Palomar 5 globular cluster. They're being pulled out from these objects during close interactions with the Milky Way. And he went on to talk more about the birth of our galaxy system way back about 11 or 12 billion years ago. He called it the Gaia-Enceladus sausage merger that began about that time, with 3 sort of proto-galaxies coming together. And so he's used Sloan and other astronomers have done this to track these streams of stars. And these are actually warping the shape of our galaxy as well, in addition to close interactions with the Large Magellanic Cloud, Small Magellanic Cloud, and the upcoming one with the Andromeda Galaxy.
Yeah. And I think what's so cool about this is that, I mean, when you show it like this, which is actually, like I said, from Price Whelan's website, it's like, oh, well, yeah, there are these, they look like they might be following like orbits around the center of the galaxy. They look like might have interacted, but these are needles in haystacks. Like they have to look at, the Gaia catalog has 1 billion stars. You've got to weed out these stars from all the other ones and say with, great certainty that they belong together. And it's a remarkable data exploration effort.
Yeah, one of the things he mentioned was that when you zero in on some of these streams, you actually see structures within the stream and substructures and areas where there aren't many stars, and then suddenly more stars. So
this is one where we can kind of see that, and that's the yeah. These points are a little large, but you can see that, and it's a real thing that these are not really evenly distributed, and they actually see sort of gaps between some of these that might be interactions. Who knows with dark matter over time, with who knows what. So,
good point. Yeah. So these streams are out there. They're finding more of them. They're probably going to find even more. And it really does, as you point out, talk to the fact that galaxy evolution really is this dynamic, changing thing, and our own galaxy is not set in a spiral shape forever, really. And there was some implication about how this affects spiral shape as well.
Well, maybe we could go back to our 3D model in our other software. But I actually forgot what our next story is. So
Desi. Dizzy.
Right.
Desi. Yeah.
Yes.
Right. So we're going to head back to Earth, right?
Yes, I think we are indeed. So let me make sure that we're targeting the right direction. Get back to Earth. Don't let you take someplace wrong. But the one of the cool results.
You can see the warp a little bit in that too. Yeah.
Sorry, let me get rid of our pulsars here. Pulsars were interesting to talk about a moment ago, but I also wanted to highlight the locations of some brown dwarfs because, talking about these amazing surveys of that help us recreate. I don't see many brown dwarfs here. I think I have a piloting problem here, so let me just try to get us back. Oh, here we are. So here we're showing a different set of jacks marking the locations of brown dwarfs. And you mentioned in passing the planet that's a little bit like a brown dwarf, and I think brown dwarfs are kind of intriguing because they're sort of this in-between sort of thing. They're not quite stars, they're not quite planets, and even how they form is kind of an interesting question.
Yeah, they used to be thought of as the leftovers of star formation. If you took the initial Nast function and said, okay, you're going to get this many stars, and then you have these black dwarfs. But I think there's quite a bit more to them than just that. So
they're fascinating, and there was a great talk that we won't get into about the atmospheres of planets and brown dwarfs and how we didn't even understand. I mean, a star is basically just glowing ball of gas. Brown dwarfs have atmospheres with clouds and like weird metallic
Structure.
things forming. It's just
Yeah.
they're crazy, crazy objects. But I think we wanted to highlight this because these, the majority of these that we're showing actually that are relatively close to home, actually I shouldn't say a majority, but many of the ones that are not described here were actually found using a citizen science project called Backyard Worlds. And I think we can bring up that website, and I think we can also share a link to it.
Yeah. It was pretty cool. This group of people. So that was part of a paper that was given because there's this whole, the DESI survey has basically whatever they used, whatever they surveyed here. People are now invited to pick through it and find things. And so this Backyard Worlds group was a group of citizen scientists, and they started looking for things, and they found more than 3,000 brown dwarfs, including one of the coldest brown dwarfs ever. And one of the things I thought was kind of funny in the press conference, they were talking about people were going through the data, and they look at each other and go, well, what have you discovered today? And somebody would say, well, I've discovered 2 or 3 things. And they're just, every time they look, they just find something. It's like this little treasure box.
And then they also talked, I think in that one, about this this cool, and actually, sorry, we can stick to the webpage, Josh, because they talked about this cool interface that they have, and we can include the URL, but to this whole collection of surveys that they assembled in preparation for the launch of this program to do a 3D map of the universe. At first, they had to build a 2D map. And we also have...
and the whole point of this also is because they're going to be using this to search out dark energy and dark matter, which seem to be ubiquitous throughout the universe. Yeah, one of the other, somebody else mentioned that they had done a talk about Xiaosheng Wang from the San Francisco, actually, University of San Francisco, used this data to look for gravitational lensing and was able to, without going into a lot of detail in this, basically able to measure light signals, if there would be like a supernova or something happening, or a brightening of a quasar in some of these perfectly aligned lenses. And he did measurements of this and was able to figure out that they basically allow him to measure the cosmic expansion rate, the H naught that we all are, the holy grail we're all seeking to perfect. So there's like 700 million astronomical objects in this viewer that people can go and just sift through. You can find lenses and supernovae and galaxies and whatever else you want to look for.
Yeah, it's pretty cool. So I was trying to show the images there of of some of the lenses, the gravitational lenses that the group here at USF has discovered.
Yeah, and they found rings and Einstein rings, and I mean it's pretty amazing. And again, back when I was first in school, these were like really rare objects.
Right.
It turns out they're not quite so rare anymore.
Bring up the image again, actually, just for
reference.
But yeah, so being able to look at these, I mean, the galaxies kind of at the center of the image are already pretty far away, but then they're warping light that's even farther away, which, like you said, gives you this sense of how the universe has actually even changed over time, which is pretty amazing.
Yeah. That's. Boy, we could go for another hour talking about some of the stuff we found,
Very cool. Well, I think
usually when we go to these meetings, we're running past each other in the hallways as fast as we can.
Right.
Getting the next press conference or the next paper. So.
Well, thanks for sharing some of your insights from the meeting with us. I don't know if we've got any questions coming through, but looks like we have one from Natalie asking about how habitable zones are predicted in binary systems.
That's a really good question.
And actually, just to give a sense of what a habitable zone is, let me go ahead and I'm going to just show the habitable zone around the sun.
Sure. Go ahead.
To make it maybe a little bit easier. And of course, I'm typical of how I'm piloting today, I'm pulling back maybe a little faster than I intended. But basically, it's this sort of sweet spot in terms of the distance from the sun, between the star and the planet. And so I'm guessing that the question that Natalie is asking is, well, what if you have a binary star?
Well, typically they're pretty far apart. I would think you probably do have a habitable zone, but it might be perturbed in some way. I got to think about that.
It's a question, because typically we talk about sort of close binary, so you might actually have two stars that are in close together and a planet orbiting both of them. Or you could have something like a planet orbiting a star and then a much more distant binary. Yeah, I guess it would depend on a lot of factors, like the relative brightnesses of the stars and their relative distance. So it's a great question.
Oh, and then there's interaction between the two stars too, so that might shove that habitable zone out a little farther if it exists at all.
Yeah, very true. All right, what kind of research equipment is being used to try to find dark matter?
It's actually across the board. I mean, yeah, we're doing spectroscopy to get the to measure the effects of dark matter on the light that's streaming from these objects. But there's an awful lot of visual astronomy that like lensing. You can look at lensing and you can tell the effect of dark matter from that. You do that with Hubble Space Telescope, for example. I've seen it, in optical visions from most of the ground-based telescopes as well. So it's kind of across the board. It's across the spectrum essentially.
Yeah, I think what is interesting about like that pulsar measurement is that it was looking at how those pulsars are accelerated by dark matter or by matter in general, and you sort of subtract out the ordinary matter to look at the effect of dark matter. And that was that's pretty cool because I was looking for dark matter very, very close to home, which is not, most of these searches, you think of looking for dark matter much, much farther from home. So pretty cool.
Well, they are basically probes of and they're using radio waves in that particular case too. They're cutting it with NRAO and radio instruments. So it really is a wide array of instruments. And I think that speaks to the ubiquity of dark matter and the effect that it has across the universe.
Well, then on the flip side too, then the physics experiments that are happening here on Earth to look for the dark matter particles to understand what these particles really even are. Sorry, I saw a question pop up, but I wasn't quick enough. So can you shed some light on scientists witnessing the death of a galaxy, 239, for the first time through ALMA?
I can't at this moment.
Yeah, that's a new one.
Yeah. Was that the AG? Was that the active galactic nuclei, the most distant one? I'd have to look that up. I'm sorry.
Yeah, I'm not remembering that. So, but yeah, that's a great question. And what we can do is we'd be happy to kind of look into that and answer a little bit later on Facebook. So if you want to check back, give us some time to do our research. We'll be happy to take a stab at answering that.
Death of a galaxy. Wow.
Yeah. Huh. Yeah, that's interesting. Well, I don't see any more questions coming through. So I guess with that, I mean, normally the American Astronomical Society meeting runs from like Monday through Thursday. So normally by this time we'd be like heading home or doing something, going on an excursion to some astronomical site close to the location of the conference. But instead, we actually have a fifth day of the conference, which is pretty crazy. So we're still in the middle of the conference in a way, or at least wrapping it up now. And so
we actually went on to the LIGO, Laser Interferometer Gravitational Observatory.
Yeah, I think I was with you.
Washington. It was pretty interesting. So.
Yes, and actually one of the trips too, I remember we got to see the James Webb Space Telescope under construction. It's like, oh, yeah, it really exists. It's there.
Yeah, you get that, yeah. People are asking, and I noticed there's been a lot of Twitter traffic today saying, yes, it really exists, and yes, it's going to launch this year. We hope. A lot of crossed fingers behind backs.
Yeah, well, these huge projects. I mean, we mentioned the Vera Rubin Observatory early in the broadcast, and with all of the challenges of building these complex instruments. So James Webb Space Telescope or the Vera Rubin Observatory kind of end up with delays almost just by the nature of the complexity of these things. But
yeah,
we shall see.
Well, we lived through that with Hubble when I was in graduate school. I was on a team, and yeah, well, and then we had to live through the whole spherical aberration problem. That was another baptism by fire. So yeah,
I like to say that I blame the Hubble Space Telescope for getting out of research astronomy, because I was dealing with that first generation of Hubble Space Telescope data with the spherical aberration, trying to do a project that just wasn't feasible.
Yeah.
Anyway. Well, again, Carolyn, thanks so much for joining us here at the Cosmic Conversations. We're going to share some URLs here on the screen, but also in chat. And you can look for Carolyn's writing on the Space Writer. And also, if you're looking for planetarium shows, you can go to lochnassproductions.com. And
I should mention that I haven't written any. I took a little break from writing on my blog, so all of my stories over the next week are going to be about AAS. So there'll be a lot more there.
Catching up. So, well, yeah, so that's great. So some of the stories that we touched on, you can read about in greater depth.
Yeah. Well, thank you for having me.
Absolutely. Thanks for joining us. And I guess I'll be seeing you at some sessions later today.
Yeah, that's true. Yeah.
All right. Thanks, everyone.